right, there we go. All right, we're back. We're back. We're doing something new. We are doing AI this time around. We did stocks, we did crypto, but now we're turning to AI. We're doing something a little bit different. We're taking a look at Cohere. Cohere is a developer of enterprise AI. They are, I believe, based in Canada. I'm not exactly sure, but you can see at the bottom here they have a bunch of top customers down here: Salesforce, Bamboo, Notion. So they definitely have a lot of big customer names. Leading enterprise AI platform. I just got a notification. First, Bamboo, Notion. So they definitely have a lot of big. All right, so let me move this. Moving a little bit. Moving the mic. Moving the mic. Moving the mic. All right. First, Bamboo, Notion. So they definitely have a lot of big. All right. Let me move this. Moving a little bit. Moving the mic. Moving the mic. Moving the mic. Okay. Give me 1 second. All right. Chapter 1, we're diving right into AI. What are word and sentence embeddings? Great picture here. Sentence and word embeddings are the bread and butter of language models. Here is a very simple introduction to what they are. This picture right here is going to give you a good overview of what this entire lesson is going to teach us. You can see on the left-hand side, it says, "Good morning. I hate Mondays. This park is awesome. This is too much. I need coffee. It's great to be out there." All of these sentences have a component that can be ranked on a scale from 0 to 10 that then helps it plot a point on a graph. So you can see good morning, it's time-based, but not really. So too much of that or too little of that is time. So morning is time, but it's not specific as to what morning, when, whatever. There is a mood component, good. And then outdoors component, right? It doesn't explicitly say outdoors. That's why it's under 5. It's 4. But we'll go through all of this on what these numbers have to do with anything, what these components have to do with anything, and you'll see how LLMs, how AIs work throughout this entire course. And this first chapter is just our starting point. Word and sentence embeddings are the bread and butter of language models. This chapter shows a very simple introduction to what they are. In old futuristic movies such as the 2001 Space Odyssey, the main computer, HAL, was able to talk to humans and understand what they would say with great ease. At the time, getting computers to understand and produce language seemed like an impossible task. But the latest large language models are able to do this in a way that makes it almost impossible for a human to tell if they are talking to another human or to a computer. The quintessential task of natural language processing is to understand human language. However, there is a big disconnection there. Humans speak in words and sentences, but computers only understand and process numbers. If we go back here, you'll see that they are assigning a number for each category or word. Okay, computers only work in numbers. How can we turn words and sentences into numbers in a coherent way? An assignment of words to numbers is called a word embedding. We can think of a word embedding as an assignment of scores to the words with some nice properties. So why are we doing this? Why are we converting these sentences and these words into numbers? It's so these computers can understand. What we'll come to see is that if we add hundreds of thousands of these components of these embeddings to these words, you start to get a picture of this word, or the AI starts to get a picture of this word that we might not otherwise have as humans, right? We can't assign all these different meanings and rank words based on meanings What we do have is we have experience with words, having heard them, having read them, having seen them be used in phrases before, and we remember this, and we try to replicate this when using words. But the AI doesn't really have a memory like that. It doesn't remember what it's used or what it's done. It might have metadata on that, but it doesn't really. It doesn't put two and two together. It doesn't rationalize the last time it used a word. But it can see and use this word in ways that we might not be even privy to based on its embedding. Metadata on that, but it doesn't really, it doesn't put two and two together. It doesn't rationalize the last time it used a word. So what is a word embedding? And before we get into what a word embedding is, let me test your intuition, says chapter 1. In the figure underneath, quiz 1, they have located 12 words in the plane. The words are the following. I'm not going to read these words out. But the question is, where would you put the word apple in this plane? They use the word locate. It's a little different, right? Because you're not putting it anywhere. It's actually, you're trying to find it. The word is embedded. So if you're this AI and you're going into this realm of worlds, realm of words. It's a back room. Words are everywhere. They're flying everywhere. And you open the door, and the AI is like, okay, everyone get in line, and it's trying to find where it would find this word apple. So there are many places this word could go, but the authors are going to only allow us 3 possibilities for where we can put this word apple. We can either put it here, where these sports balls are. We can put it here with these other fruit. We can put it at B, where it looks like houses and structures. Structures, or could put D, right? Not so much close to transportation, but somewhere in the middle between transportation and fruit. Well, I don't think it's a house. I don't think an apple's a house unless we're like a worm or something. And I don't think it's a means of transportation. It is somewhat round, but I don't think it's a sports ball. So we're going to play it safe and go C, because that's where all the fruit are. What I would do is locate it in point C. Okay, fair enough. Because it would make sense to have the word apple close to the words banana, strawberry, and cherry, and far from the other words such as house, car, or tennis. This is precisely a word embedding. And what are the numbers we're assigning to each word? Simply the horizontal and vertical coordinates of the location of the word is what these numbers mean. So in this way, the word apple is assigned to the numbers 5, 5, and the word bicycle to the coordinates 5, 1. Now in this graph, by itself, we don't know what these axes mean. The one on the left could mean, I don't know, size, and the bottom one could mean color. We don't know. But these numbers, as we'll see, are going to represent what we saw at the beginning, right? They're going to represent different elements for each, for each word and for each sentence. And the closer that each word or each sentence is closer to these describing words is where we'll find it plotted on a graph like this. For the sake of redundancy, let's enumerate some properties that a nice word embedding should have. Words that are similar should correspond to points that are close by, or equivalently to scores that are similar. And words that are different should correspond to points that are far away, or equivalently to scores that are significantly different. Word embeddings capture features of the word. The word embedding above satisfies properties 1 and 2. Is that it? Not yet. There is something more to these word embeddings, and it is that they don't only capture word similarity, but they also capture other properties of the language. In language, words can be combined to get more complicated concepts. Yeah, in language, words can be added or subtracted to get other numbers. They can be combined to get more complicated concepts. Could we build a word embedding that captures relations between words as relations between numbers? Now it's saying, can we create similarities between words just as easy or just as representative of seeing them plotted on a graph? So is, dog similar to cat as 1 is similar to 2? And we'll see. So let's look at 4 words: puppy, dog, calf, and cow. These words are clearly correlated in some way, some form. They're all animals. But to test our intuition, they're going to let us locate the word puppy, dog, and calf in the plane. And I'll ask you to add the word cow. Where would you add the word cow? Either A, B, or C. Excuse me 1 second. So we have the word cow, and we want to locate it on this map. On the left we have calf, so it could be A, right? It could be A, but cow is an adult calf, whereas dog is an adult puppy. So we don't want to put it at B because B looks where the dogs are, but it does have a similarity to calf, and it also has a similarity to dog. So why don't we stay C again? Well, let's stick C. While it would make sense to locate it in A, closer to calf since they're both bovine, or in B since it's an adult animal like dog, the place where I would put this is in spot C with the coordinates 3, 4. Why? Because the rectangle formed by the 4 words captures some very important relationships between them. For instance, two analogies are captured here. The analogy a puppy is to a dog like a calf is to a cow can be translated into the path from the word puppy to the word dog is the same as the path from the word calf to the word cow. The analogy a dog is to a cow like a puppy is to a calf is also captured in this rectangle as it's shown in the figure below. However, this is not the tip of the iceberg. The main property of word embeddings that is in effect here is that 2 axes, vertical and horizontal, represent different things. If you look carefully, moving towards the right turns the puppy into a dog and the calf into a cow, which is an increase in age. Likewise, moving upwards turns a puppy into a calf and a dog into a cow, which is an increase in the size of the animal. It seems that this embedding is understanding that the words in it have 2 main properties or features, age and size. So what this graph is saying is that the bottom axis more than likely represents age. So puppy's at 1 and dog is at 3. So the more we move along this horizontal axis, we can see that the animals get older. And then from horizontal or from vertical, we can see there's also size, right? So we can see that 1 of 1 puppy is small, where we go to 4 1 calf. Calf is a bigger animal than a puppy, but it's still a child of an animal, right? So bottom being age and vertical being size is what this grid is embedding on. Furthermore, it seems that this embedding is locating age in the horizontal axis and size in the vertical axis. In that case, where would you imagine that the word whale goes? Probably somewhere above the word cow. And if there was a word for really old dog, that word would go somewhere to the right of dog. A good word embedding would be able to capture not only age and size, but also many more features of the words. This is what I'm talking about. You can embed a word based on thousands or hundreds of categories. And so since this new feature is one new axis or coordinate, then a good embedding must have more than 2 coordinates assigned to every word. We can, again, go into 1,000. One of the cohere embeddings, for example, has 1,024 coordinates associated with each word. So Cohere, the nice company, the nice LLM producer who created this training, they have 1,024 embeddings. So 1,024 categories that they are tagging to each word. 1,024 categories. Age, time, weight, anything that is in these 1,024 is how they're weighing these words, embedding them, so that these LLMs, these AI models, can go in and find the words to use based on context of sentences and questions. These rows of 1,024 of these coordinates, these rows are called vectors. So we often talk about the vector corresponding to a word and to each of the numbers inside a vector as a coordinate. Some of these coordinates may represent important properties of the word, such as age, gender, and size. Some may represent combinations of properties, but some others may represent obscure properties that a human may not be able to understand. But all in all, a word embedding can be seen as a good way to translate human words, human language. So you're translating human language, this thing that is arbitrary, this thing that is how we communicate, essentially made up. And different between languages, right? Not the English and Spanish, the words are different. They might have similar meaning, but the words are completely different. So these word embeddings can be used to translate human language, words, into computer language, numbers. So we're translating words into numbers, a way for something that we use to communicate into numbers so the computer can understand. And this is how we get to start training machine learning models with these numbers. So again, on the left, you can see here's the word. Here's the associated numbers. Again, this is only 2 columns for our example, but then on the right, we go from 1 to 1024 different embeddings, different coordinates. So just like we can embed words, we can embed sentences as well. Word embeddings seem to be pretty useful, but in reality, human language is much more complicated than simply a bunch of words put together. Human language has structure, sentences, etc. How would one be able to represent, for instance, a sentence? Well, here's an idea. How about the sums of scores of all the words? For example, say we have a word embedding that assigns the following scores to these words. No, I am good. And there's the different coordinates of how it's ranking and rating each word. The sentence no, I am good corresponds to the vector 0, 2, 2, 3. However, the sentence I am no good will correspond to the vector 0, 2, 2, 3. This is not a good thing since the computer understands these two sentences in the exact same way, yet they are quite different. Remember, because these sentences are using the same words, but the implication or the reasoning for these sentences, what they're trying to say, are very different. Therefore, we need better embeddings that take into account the order of the words, the semantics of the language, and the actual meaning of the sentence. This is where sentence embeddings come into play. A sentence embedding is just like a word embedding, except it associates every sentence. So take exactly what we did for the word and move it to the sentence. It associates every sentence with a vector full of numbers in a coherent way. By coherent, I mean that it satisfies similar properties as a word embedding. For instance, similar sentences are assigned to similar vectors, different sentences are assigned to different vectors, and most importantly, each of the coordinates of the vector identifies some, whether clear or obscure, property of the sentence. With 1024 embeddings and different coordinates, I'm sure there's going to be embeddings and coordinates that are not going to make sense to us at a glance. If you were writing notes, right, you might write a different note about something than someone else. And so that is exactly what these LLMs or these models are doing. They're embedding, they're learning about these words, and they might be using a rating system or a number system and embedding metric that doesn't align with how a human or how someone else may conceptualize a word or a sentence. The cohere embedding does just this. By using transformers, attention mechanisms, and other cutting-edge algorithms, this embedding sends every sentence to a vector formed by 4,096 numbers, and this embedding works very well. Again, so cohere is taking from a word where it uses 1,024 embeddings, going to sentences where it uses over 4,000 embeddings to help store and process different words and sentences as it's being used. And it may use different schemas or different places to store this information, right? If someone just puts a word versus someone puts a sentence, it's going to need to go to two separate areas, but that sentence knowledge is still going to rely on the knowledge from the word. So they're going to have a way to interact. As a small example, here's a heat map of an embedding containing 10 entries for each sentence. For several sentences, writing the entire 4,096 entries will take too much space, so we compressed it using a dimensionality reduction algorithm called principal component analytics. So again, the embedding is the thing, or the words that we're rating these sentences and these words on, and we don't know what these values here mean, what the vertical and the horizontal mean, but we can see that the value, when high, means that it's supposed to be in this particular space. And from what we can see here, of all the we'll take the darkest square. Of all airlines, which airline has the most arrivals in Atlanta? And then we'll look what's also on 5. Which airlines fly from Boston to Washington, D.C. via other cities? Okay, so we could technically see that this has airlines, it has cities, and it's also asking a question. So that could mean that is why they are very similar. Notice that these sentences are all very similar. In particular, the 3 highlighted sentences pretty much have the same meaning. Show me a list of ground transportation at Boston Airport. Show me Boston ground transportation. What ground transportation is available at Boston? If you look at their corresponding vectors, these also seem very familiar. This is exactly what an embedding should do. How to use these embeddings. Now that you've learned how useful these embeddings are, it's time to start playing with them and finding good practical use for them. The Cohere dashboard provides a very friendly interface to use them. Here's a small example with the following phrases. There's the phrases. To see the results of the sentence embedding, go to the Embed tab in the Cohere dashboard and type the sentence. We're not going to do this test because they have an output here for us to look at. These results come out as vectors with 4,096 entries for each sentence. These are obviously hard to visualize, but there's a way to bring them down to 2 entries per sentence in order to easily be visualized. This visualization is shown in the plot below. So we can already see there's some clustering going on. We can see in the top left we have greetings, hey, what's up, hello, how are you, hi, how's it going? In the bottom we have something to do with a way a person is feeling about their animal, or even just dogging the situation. And then in the bottom right we have someone who likes watching soccer. Notice that the embeddings seem to capture the essence of the sentences. And there are 3 clear clusters of sentences. That's a tongue twister for you. In the top left corner, you find the sentences that a great person, in the middle, those that talk about a person's dog, and in the bottom right corner, or not a great person, how to greet people, those that talk about soccer. Notice that sentences such as, hey, what's up, and hello, how are you, have no words in common, yet the model can tell that they have the very same meaning. You can kind of see how this is starting to take place for LLMs, how they can come up with responses, how these Gen AI, go to ChatGPT, how they're coming up with responses to questions or queries that are given to them, right? When you're typing in and you're sending it to ChatGPT, on the back end, it's tokenizing, it's taking these words, it's looking at each word individually, looking at their embeddings, then it's looking at the sentence and looking at the sentence embedding and saying, okay, what do I got with this? What do I got close to it? What are they asking me? And then going through its archive of stored results and giving you an output, giving you a response to your question based off of the embeddings that it has. Multilingual sentence embeddings. Most word and sentence embeddings are dependent on the language that the model is trained on. This is where language comes into play. It is so key because an AI model, can dive through, it can break up, it can look through the difference in language. It can break the barriers. It can break down communication issues because the model, because it's ranking, it's embedding, it's putting these words in separate places, it can tell the meaning of the words in these different languages. And because embeddings are based on these coordinates of how a model thinks a word is going to be used or where it's going to show up, it cuts through the translation error. And you can even ask it a question and tell it to respond to you in a different language because it's storing the semantics, it's storing the meaning of these words and these sentences, regardless of language. And it's all stored on a similar graph, on a similar plane that you see below. So all these phrases, all these different words are going to be bundled in the same area, even though they're in different languages. Because remember, if we're doing words, we have, for Cohere's model, 1,000 different embeddings. And if we're doing sentences, we're doing 4,000 with Cohere's model. Here's all those same sentences in English, and you can see it kind of bundled them in the same way. So what is our conclusion? What are we coming to find out with this? What have we learned in the first chapter of Cohere's LLM University about sentence and word embeddings? The conclusion: word and sentence embeddings are the bread and butter of LLMs. They are the basic building block of most language models since they translate human speak words into computer speak numbers in a way that captures many relations between words, semantics, and nuances of the language into equations regarding the corresponding numbers. Sentence embeddings can be extended to language embeddings in which the numbers attached to each sentence are language agnostic. These models are very useful for translation and for searching and understanding text in different languages. Now, that was the first lesson. What are word and sentence embeddings? The next lesson, or not tomorrow, I think we're doing Thursday. The next lesson would be what is similarity between sentences. But I want to take a pause on what we learned today, and I want to just leave a note in that we can see how LLMs associate all these words, all these sentences with one another based on these embeddings. And if these AIs, if these LLMs, if these Gen AIs can make these correlations, they can see what's similarity between words and phrases and sentences and languages, they might be able to see more in how our language works than humans can or have at any point in history. We don't look at the words in the same way. We do have linguists that break down semantics and syntax and why certain things are said or how they're said and inflection, but the AI is processing all this and all these minute data points. It might be able to see, again, we don't know, but we can assume based on numerical properties, what is the optimal thing to say in certain situations? What is the optimal thing to say to get one response over the other or one outcome over the other? And so we might in the future be able to see these LLMs, these AIs, making autonomous decisions, making decisions by themselves without input from a user, from a query. When you have these autonomous AIs, these LLMs, going to ask questions or going to do things in a certain way based on the way that their embeddings are set up, because they understand these sentences and the meanings behind these words in a different way than a human or you or I may have. And so that is chapter 1 of our LLM University module. We're going through all of these, and that is chapter 1, what are words and sentences, or what are word and sentence embeddings. So you can see here there are 9 modules. It looks like there's about 4 to 9 in each section, and we will be going through all of these. And so by the end, I hope you all take away something that you did not know before. I hope I take away something I didn't know before. And I hope everyone is able to learn and grow from this because AI and LLMs are here to stay. They're not going away. It is something that is going to change the way that we operate and the scale at which we grow over time as a civilization. And learning how they operate, learning what goes into an LLM and how they work, how they function, will help us better understand what we need to do or how we need to act as humans with regards to AI, because we get it. We understand how they process things, and it'll help us leverage them better to our advantage. So that is Monday's episode, chapter 1, what are word and sentence embeddings. Thank you for joining us on this journey. Catch you next time for chapter 2.